Bam! Mr. Tarrou. In this calculus lesson, we're ultimately going to do 3 examples determining the interval of convergence of a power series. What's a power series? Well, it says here, if f is a variable, then an infinite series in the form of the summation where n starts at 0 and goes to infinity of a sub n times x minus c raised to the n power is equal to a sub 0 plus a sub 1 times x minus c raised to the first power plus a sub 2 times x minus c raised to the second power, and we keep adding and so on until we get to the nth term, and then, yeah, we just keep adding because this is the series. You know, n goes to infinity. We never stop adding these terms. And this is a power series centered at a constant c. Now, if I were to come through here and take out all these variables, or this, not really a variable, but this constant of c, and just have it set equal to 0, then that would be a power series, centered at 0. But this is the more general form. So one thing to note here, because now we're talking about, you know, convergence and divergence, and we have these sigma notations or these summations expressions showing up, not the sort of standard looking series that we've been working through in our previous sections. We talked about ratio and root test and alternate series test and so on and so on. But you'll see here that when we go from the summation notation into our expanded series notation, the variable of n is gone. That's starting at 0 and going to infinity. We have a function that is in terms of x. So when we are trying to determine the interval of convergence, what we're actually trying to determine is when we plug in some value of x, we get a series, and does that series converge or diverge? Do we get a real sum from that series? If we get a real sum, that occurs, right, when our series converge. And so if we get an actual sum for the series, if this series is converging, well, then this is going to give us, right, that valid, well, it says right here, sum. So we are, oh, and by the way, you can kind of notice when you see an expanded series like this, if you have a variable x raised to some power, that's when you identify and you can go, okay, that is a power series. This series converges, like I just said a second ago, if this series converges, we get a valid sum. We are determining for what values of x does that summation give us a valid sum. We are looking for the domain of all x's such that this series right here converges. If it converges, we get a valid sum, we're good to go. If it diverges, well, then our sum would be something like infinity or undefined. That's not what we are looking for, but that's hopefully giving you a good understanding here, an idea of what is going on. Now, to do these 3 examples, we're going to use that ratio test. We just talked about that in the previous section. Because that ratio test says that a series absolutely converges if the absolute value of the ratio of a sub n plus 1 over a sub n is less than 1. If it's equal to 1, it's indeterminate. If it's greater than 1, then that series diverges. So the ratio test gives us an inequality to work off of to determine that interval of convergence. So as I read through here what we're looking for, and I'm talking about radius of convergence, I'm talking about doing that ratio test to this series, and we're going to make sure that that ratio stays less than 1. If the radius of convergence is equal to 0, then the power series is going to be said to converge only at that constant, at that c, the center of that power series. If the radius of convergence is infinity, and I'm pausing because I'm going, okay, I want to say the 0 and this infinity, and then finally the condition here with the outcome number 3, if you will, is that result again of setting up the ratio test and looking at ultimately what we're arriving at. It'll be clear as we do the examples. If the radius of convergence is infinity, then the power series converges absolutely for all x. It doesn't even matter what x is. So these 2 types of solutions will be example 1 and 2, and they're not quite so interesting because there's no work in determining what that interval of convergence is. Now, if we do the ratio test, we set that up, and there exists a real number r that's greater than 0. So not 0, not infinity. That's where the little bit of extra work, that's where the skills that we learned in all these previous sections, learning all these tests, alternating series tests and direct and limit comparative tests, so on and so on, come into play. Well, if there exists a real number r greater than 0 such that the series converges absolutely for the absolute value of x minus c is less than r, and diverges for the absolute value of x minus c is greater than r. We're going to be focusing really on this part here. When you get the absolute value of some binomial alone, and it's less than, well, whatever your radius of convergence is going to be, we'll be able to identify what the center of our power series is if we can't already see it in the expanded form. And for the three examples that we're going to be doing, we're going to have our series written like in this format here. And we'll have our radius convergence. Now from there, we're going to find that we'll have found that radius of convergence. And then we're going to test whether the power series converges or diverges at the endpoints of your interval. That's where maybe you need to, once you plug in some particular x values into the series, start looking at it and trying to go, okay, was this harmonic, alternating harmonic series? Is it a geometric series? Is it something that we need to do some kind of limit comparative test to? We need to determine whether this series converges or diverges at the endpoints of our interval to come up with our final answer. Now, this is a lot of words and writing, and hopefully kind of makes sense, but I think doing these three examples is going to clarify this up for you. The first one coming up right now. Alrighty, our second example, we're going to look for the interval of convergence of this series here. We have n, the summation of n starting at 0 going to infinity of 4 times x to the n power over 2n factorial. And I did a little bit of expansion here just to let you see that we again have that function in terms of x. We're finding the domain of this function such that it gives us a valid sum, such that it converges. So we're going to set up that ratio test. And by the ratio test, we have the limit as n goes to infinity of a sub n plus 1 over a sub n. Again, instead of dividing by that fraction, we're going to bring it up as a multiple of a reciprocal and clean things up. This factor of 2n factorial, now that we've done a little bit of expansion on that factorial notation, is going to cancel out with 2n factorial. In the denominator of our second factor, we have n bases of 4x. Here we have just one more, so this is going to cancel out and leave us with just one factor of 4x in the numerator. And this is really kind of simplifying, very similar to the previous one, but we have a lot of n's now in our denominator as opposed to the numerator of our last one. Now, if we let n go to infinity, well, we're going to have 1 over infinity, which approaches 0. And 0 times 4x is just 0. So the limit here, I was going to write it on the second line, but I don't need any extra room to write 0. The limit as n approaches infinity is 0. And of course, 0 is always less than 1. So since 0 is always less than 1, and there's not even a place for x to go, right? So for all x on the interval from negative infinity to positive infinity, so therefore, by the ratio, So therefore, the given series converges absolutely for all x. I'll be right back. And for our third and last example, we have the summation where n starts at 1 and goes to infinity of -1 to the n plus 1, which means that we are looking at an alternating series, by the way, times x minus 3 to the n over n times 7 to the n power. Okay, so we're looking for the interval of convergence of this series, this power series, which means that by the ratio test, we are looking at the limit as n approaches infinity of a sub n plus 1 over a sub n. Now we put this in the notes earlier, but how is it, how do we look at this and, how can we tell that we have a power series? Now, maybe you could expand it a couple of terms to make sure, let those n's kind of disappear and look at what your expansion looks like, because you're only going to have that variable x. You have a function in terms of x, and you have an x raised up to some power. That power, of course, is going to be increasing as we let n go from 1 to infinity. So that variable x raised to some power is your indication that you're looking at a power series. Okay, as always with the ratio test, we're going to multiply by the reciprocal and clean things up. Lots of cancellation. So the limit as n approaches infinity of the absolute value of the -1 raised to the now n plus 2 power, because of course 1 plus 1, times x minus 3 raised to the n plus 1 over n plus 1 times 7 to the n plus 1 power. Multiply that by the reciprocal of the denominator. We have n times 7 to the n over -1 to the n plus 1 times x minus 3 to the n power. Okay, so we have n sevens in the numerator of our second fraction and n plus 1 in the denominator of our first fraction, leaving you with one factor of 7 in the denominator. We have x minus 3 to the n and x minus 3 to the n plus 1, just one more factor in the numerator. And the same thing here, too. We have -1 to the n plus 1 and -1 to the n plus 2. Well, 2 is just one more than 1. Now, cleaning this up, what do we got? We have the limit as n approaches infinity of the absolute value of, well, and actually, let's do this. Let's take out all those n's because they're going to be positive. The absolute value, again, is going to take care of that factor of -1. We have an n, so the limit as n approaches infinity of n over, that's this one right here. In the denominator, we have a factor of n plus 1. And we can bring that 7 out as well if we want, or we can leave it, inside the absolute values. I think I'm going to leave it inside the absolute value. Not that the absolute value of 7 is just going to be 7. So we have, let me just make sure I didn't copy something down wrong. Absolute value taking care of that, -1. We have our factor of x minus 3 here. We have a 1 over 7. The absolute value, the n is starting at 1 and going to infinity, so it's never going to be negative. Pulling that out in front of the absolute value sign, just giving this a little bit of a different look. The limit as n approaches infinity is this n over n plus 1 is going to come out to be 1. So we have that this is equal to the absolute value of 1 over 7 times x minus 3, the absolute value of all of this. And remember, we are looking for the domain of this function, well, actually this function when it was expanded, that, the domain of x that makes the function converge so that we have that valid sum. So that with the ratio test says that the absolute value of the ratio of a sub n plus 1 over a sub n must be less than 1 for that to absolutely converge. And the absolute value of 1/7 is 1/7, so actually I could go ahead and bring that out. And at this point, like I mentioned earlier in the notes, once you have that x minus c, the absolute value of x minus c is less than, well, I don't have quite the absolute value of symbol alone yet, so I'm going to multiply both sides by 7. And we have the absolute value of x minus 3. I almost started talking there, could you tell? And say something that was incorrect. we have 1 times 7 is equal to 7. Now here's at the point you can look at this and go, hey, the center of our power series is 3. And here we have that capital or that real value that's greater than 0. We have a radius of convergence of 7. Okay, so we have now a result that is going to allow us to set up a preliminary interval for convergence, but then we're going to have to test the endpoint. So let's go ahead and write this without the absolute value signs, which means that this can be, well, if the absolute value in the 7, this can be like 7 or negative 7, but it has to be in between those values. So we have negative 7 is less than x minus 3, which is then less than 7. Solving this compound inequality, we're going to, very difficult here, add everything by 3. And we have negative 4 is less than x, which is less than 10. So our interval, I can't say really interval of convergence because we haven't tested the endpoints yet, but our preliminary interval here is from negative 4 to 10. So now we need to test the endpoints. And I'm going to try and squeeze this down in here. I'll pick a different color so you can tell the difference of what I'm doing. Test the endpoints. Very easy for students to forget this part. My textbook that I teach from even acknowledges, hey, don't forget to test the endpoints. So what about when x is equal to negative 4? I'm really afraid I'm going to run out of room here, but we're going to be looking at the summation where n goes from 1 to infinity. And I'm just going to take out the x and plug in negative 4. So negative 1. N plus 1, parentheses, negative 4 minus 3 to the n power over n times 7 to the n. Now here's at the point that, there's some simplification that we can go through, but here's where the point that you might find out that a lot of these become very easy to determine whether they converge or diverge, but you might need to lean on those, start pulling those toolboxes out. You're going to use maybe a p-series test, the alternating series test, integral test, limit comparative test, direct comparative test, root test, ratio test. Here's where we come in and we have to use all of those tools and know which one is appropriate. And many of these, when you test whether series converge or diverge, most of them have more than one way to figure that out. But what do we got going on here? We have the series negative 1 to the n plus 1. Negative 4 minus 3, of course, is negative 7 to the n. And we have n here with a 7 to the n power. So we have a negative 7 to the n, and in our denominator we have positive 7 to the n. Looks like we could almost make those things cancel out, right? And what's the square root of 2 times the square root of 3? Well, that's just the square root of 6, right? You can multiply inside. Well, what do we have here? We have 2 to the 1/2 power times 3 to the 1/2, and that's 6 to the 1/2. So we can multiply together 2 times 3 is 6, and in reverse, factor that 6 to be 2 times 3 within those matching rational powers. In this case, well, in this case, are rational powers. In this case, we just have n. But I'm just pointing it out to validate for you here that I can take the negative 7 to the n power and write it like this. Basically just factor it. So we have negative 1 to the n times 7 to the n over n times 7 to the n. Well, check this out. Now, if I rewrite that 7 as negative 1, oops, and I forgot the plus 1 here, as negative 1 times 7, well then the 7 to the n power over 7 to the n power, these are all factors. Those common factors will cancel out. We have a multiplication of like bases, well, when you multiply like bases, you get to add those exponents, and n plus n is 2n. So in the numerator, we're left with negative 1 to the 2n plus 1 over n. And 2n plus 1, I think you're probably pretty comfortable by now. If you take a number and you double it and you add 1, you're guaranteed to have an odd answer. And negative 1 to an odd power is always going to come out to be negative 1. So this looked like and was an alternating series. But when we check the endpoint where x is equal to negative 4, we actually get negative 1 times the summation, where n starts at 1, goes to infinity, of 1 over n. So it's negative 1 times the summation of a harmonic series. And harmonic series are divergent. So when we tested our endpoint of x equals negative 4, at negative 4, this series diverges. So that is not going to be included in our final interval of convergence. Now let's check the 10. And I did run out of room, so hopefully this is okay. I'm going to go ahead and erase this. So I should have went ahead and just erased all of it, huh? All right. Taking that x value of 10, plugging it in, what do we got? We have negative 1 to the n plus 1 times 10, not n anymore, or x for that matter, 10 minus 3 to the n power over n times 7 to the n. Well, of course, 10 minus 3 is 7, and our 7 to the n power, like the previous one, 7 over n divided by 7 over to the nth power, is equal to 1. And this time, well, this simplification for when the checking the endpoint of x equals 10 comes out to be really nice and simplifies very quickly. We have the summation where n starts at 1 and goes to infinity of negative 1 to the n plus 1 over n. Well, now this negative 1 to the n plus 1, that's going to, well, it's going to go between positive and negative. And thus we have an alternating harmonic series. An alternating harmonic series, unlike the regular harmonic series, converge. So we took our original power series, we set the limit up, we did the ratio test, set the limit up as n approaches infinity of a sub n plus 1 over a sub n. We did a lot of simplification. Unlike the previous examples, the two examples, we did get x minus 3, the absolute value of x minus 3 or x minus c is less than some real r, which is greater than 0. In this case, it was 7. So our center is 3, our radius of convergence is 7. We went ahead and wrote that as a compound inequality. We solved, found an preliminary interval of convergence, checked the endpoints. Negative 4 didn't work in the sense that it came out to be, that series came out to be divergent, but 10 did, at x equals 10, our series did converge. So our final interval of convergence, and just to, because I'm running out of space here, this is our interval of convergence. So again, if you take these x values, starting from but not including negative 4, up to 10, plug them into the function that you get as you expand out the summation notation, because all the n's would go away. This is actually equal to a function in terms of x. Plug these values of x into that function of x, that expansion of that summation notation, you will get a series that converges. This is the domain that allows this series to converge, thus giving you a valid sum. I'm Mr. True. Bam! Go do your homework.